Actually, we have looked at once before, but I think it will help us to be able to handle some of these situations. For every A and B and C belonging to the set of real numbers where C is not 0, A divided by C plus B divided by C is equal to, and of course everyone says, Doug?
A plus B divided by C.
A plus B all over C. All right? Now, I don't want to prove this again. We've already gone through the proof of that. But what I'd like to do is to look at another theorem in which, notice here that the denominator C is the same. And that's really what we were relying on. And let's look then at a theorem in which we have for every A and B and C and D belong to the set of real numbers, where B is not 0, and let's allow D not to be 0. And let's see what we may say. Suppose we have A over B plus C over D. In this case, now we have different numbers in the denominator. And I'm not sure that anybody can pull this out of this hat as to exactly what this is going to be equal to. But what can anyone say anything, Peter?
AD.
A times D
Plus BC.
Plus B times C.
Over BD.
All over BD. And in fact, this is exactly what the result of the theorem is. And let's go through the proof of this to make sure that that's indeed the statement that we want. All right, here's our statement and the reason for that statement. And let's start out on the left-hand side with A over B plus C over D. And let's see what we may say about this. Now, what I'd like to do is to simply indicate that this is times 1. A over B times 1 plus C over D times 1. And of course, our reason for this is simply what? This is our multiplicative axiom of the number 1. Is that right? Our multiplicative axiom of 1. Now, what I'd like to do is to look on the right-hand side here at this number 1. And A over B times 1, certainly, we have an infinite number of names for the number 1. Is that right? Now, out of all of that infinite number of names, which one would you like to use? And Doug?
D over D.
D over D, all right? D over D. Plus, and now here we have C over D times 1. And again, there's an infinite variety of names for that number 1. And which one would we like to use here, Kirby?
B over B.
And you'd like to use B over B as that name for the number 1, okay? And of course, the purpose in doing this is to get back to the first theorem that we have just used, in which now here we have the same denominator, namely BD. What's our reason for saying this, by the way? Let's see, we have 1 then is equal to D over D, and 1 is B over B. And what then would be our reason for that? Perhaps we could use what property there, Tim?
Substitution.
Substitution, I'm not sure that that would be the best reason for saying that. Let's see now. If we thought in terms of D times 1 over D here, and we know that D times 1 over D is 1, that would be what? What is our property which enables us to say that, Brenda?
Reciprocals.
Our reciprocal. Property of reciprocals, I think, would be a legitimate reason to use here. Now, let's then use that theorem that has to do with AD over BD plus, oh, let me use a little bit of commutativity here, BC over BD. And what we're really doing is using the theorem that has to do with property of quotients. Is that right? And let's indicate that as our reason for this, our property of quotients. And of course, now as soon as we have it written in this pattern, immediately then we may put it over that same denominator of BD, and we have AD plus BC divided by BD. And let's see, I guess the reason that we can use for this is the theorem stated above. Oh, let me just write it as x over z plus y over z is equal to x plus y over z, where that's the pattern that we are concerned with, all right? We haven't really given it any name. And have we proven this theorem? Are we done? All right. And notice then that when we have different denominators here, by the way, what word did we use to describe this denominator that we have here? There was a phrase that we used, in the past, in which we call that, what, Brenda?
The common denominator.
The common denominator, and in fact it is the Bill?
Least common
The
denominator.
least common denominator. And the method of proof in this theorem is in fact exactly what we're going to do in a few examples. So let's look at a number of examples. Here we have x over x minus 1 minus 3 over x plus 1. Let me work in a vertical fashion here. Now, what I'd like to do in the first example is to put in all of the steps as we have in this one that we have just done, and then in fact I'd like to streamline it a little bit. Well, here we have x over x minus 1 times 1 minus 3 over x plus 1 times 1. And now let's then look at this number 1, x over x minus 1 times, and what name for the number 1 would you like to put in here? And again, Glenn?
X plus 1 over x plus 1.
All right, does everyone agree that x plus 1 over x plus 1 is going to help you get where you want to go? And then here we have minus, there's 3 over x plus 1 times, and now what name for the number 1 would you like to put in this place? And Michael?
X minus 1 over x minus
X minus 1 over x minus 1 then is going to help you there, because notice then that here we have this denominator of x minus 1 times x plus 1. The numerator is x times x plus 1, and then minus, and now here we have the same denominator, and the idea is to get back to that first theorem in which we have the same denominator in both cases. And in fact, the name that we give this is called the what? This is our least common denominator. Is that right? And now we'll use that first theorem in which we have it all over that number c. And now in the numerator, well, let's actually multiply this out at the same time. And we have here what? X times x plus 1 is what? X squared plus x minus 3x plus 3. Is that right? And let's see, then we can clean up that numerator a little bit. X minus 1 times x plus 1 is still in our denominator. And here we have x squared. X minus 3x is what? Minus 2x plus 3. And you'd better look at that a second time and ask yourself, can I factor it? And the fact that this is a minus sign, but that this one is a plus, I think should tell you that it is non-factorable. Is that right? We cannot reduce it anymore. So in fact, this then would be the most simple name for this original expression. Notice there we have added or subtracted these fractions, okay? And we have it written in this pattern right here. Well, let's look at another example. And in this case, perhaps we don't need to put in every one of these little steps. And let's see if we can streamline it a little bit. Here we have y over x squared plus xy minus 2y over x squared minus y squared. And you look at that and you say, well, in this denominator I can factor out of there what? An x, and we have x times what? X plus y minus. And here we have 2y divided by what? We may factor that into, Brenda?
X plus y
X plus y
times x minus y.
times an x minus y. Good. Now, rather than putting in that number 1 in each case and looking for another name for that number 1, let's streamline this, if I may use that word, and go right to that least common denominator. So what then is going to be that least common denominator? And Bill?
It's going to be x
X
times x plus y
times an x plus y
times x minus y.
times an x minus y. Good. X times an x plus y times an x minus y is that number for which when we divide each one of these denominators into that denominator, certainly we then will have the remainder of 0. Is that right? That's really what we're saying. Well, in the numerator then, now here, think in terms of that number 1. X times x plus y times what number gave you this denominator? And that other number is x minus y. And so for that number 1, that's the denominator, so therefore the numerator must also be what? X minus y. Is that right? It's x minus y divided by x minus y here. So we then have y times x minus y. Is that right? Minus, and now here we have 2y times some number. Well, that number has to be the same number as you have when you multiply this through by some number in order to get this denominator. So what number then are you multiplying through in this fraction, in this denominator, in order to get this denominator, or least common denominator? And it is, Doug?
X.
Times x. Is that right? Everyone agree? So we then must multiply that numerator by x. Okay, now let's then try to simplify that numerator a little bit. We still have the same denominator here. And here we have in our numerator what? There is Well, let's just multiply that out. We have what? xy minus y squared minus a 2xy. Is that right? And you look at that and you say, well, I have there xy minus 2xy is the opposite of x. So let's write here the opposite of y squared minus xy. All right, let's put in an extra step. Times an x plus y times an x minus y. Now you look at this numerator and you say to yourself, if I can only factor out of there some number such as what? As y. How about the opposite of y? Good. So if we then were to take out the opposite of y, what's left but y plus x, which perhaps we would rather write as x plus y. Good. Let's write that as x plus y. And you look at this and you say, aha, the problem is rigged. Because now we're right back to the case that we had in our previous assignment, in which there's now a name for the number 1 still hidden in there, namely x plus y over x plus y. Therefore we have the opposite of y over x times x minus y. Now whether you leave your final result written in this pattern, in which you still have a factor here, or else you were to then say, oh, let's keep the opposite of y up there, and think of this as x squared minus xy. In this pattern, it's a matter of personal taste and preference. Both of these are perfectly acceptable results. Okay? Well, let's look at another example. And here we happen to have 3 fractions. All right? And so you say, well, that shouldn't disturb us. Let's just see how we may go. 2b plus 1. Now notice here that this denominator, before you plunge in and try to write things down, notice we have 2b plus 1 and a 4b squared minus 1, and you say, by golly, that will factor into what? 2b plus 1 times a 2b minus 1, but here we have 1 minus 2b. So I don't want to write 1 minus 2b. It would be nice to write this as what? 2b minus 1. Well, we just can't go around making that 2b minus 1. What have you done to 1 minus 2b in order to get 2b minus 1? You have taken its, Kirby, its opposite. So if we were to take the opposite of this denominator, we would like to take another opposite somewhere, and the obvious place is where? In the, well, in the numerator certainly, or how about this sign here, from a plus sign to a minus sign, we then will have taken its opposite. Is that right? The opposite of this opposite then is what we started with. And we still have 2b in the numerator minus, and we still have here 3 over, in fact, let's actually write this as factors, namely what? This is 2b plus 1 times 2b minus 1, and right there you have set it up so that you can write in your least common denominator, which is, Charles, there's a 2b plus 1
Times 2b minus 1.
times a 2b minus 1, and you're all set. Now, 2b plus 1 times what number is this denominator here? It is what? 2b minus 1. So I have to multiply that numerator by that same number of 2b minus 1. Is that right? Minus, and now 2b times what number? All right, must I have here? Well, it's that same number which I had to multiply 2b minus 1 by in order to get this denominator, namely 2b plus 1. All right, minus, now this number, this denominator, times what number is this denominator right here? 1. So therefore, 3 times 1 is 3. And we still have that number 3 is equal to, well, let's try to clean up that numerator a little bit. We'll include this same denominator, and let's just multiply this out and collect terms in our next step. We have here what? 6b squared minus 3b minus 4b squared minus 2b minus 3. Okay, now let's see what happens there. 6b squared minus 4b squared is 2b squared minus 3b minus 2b is minus a 5b minus 3. And you look at that, and by this time you're quite suspicious, and you say, I'll bet I can factor that, in which we have there what? Well, let's try 2b times a b is a 2b squared. What number can we put in here? A minus 3 and a plus 1 will then give us a negative 6b, plus b is a negative 5b, and a negative 3, and sure enough it factors. we have there, oh, look at this, 2b minus 1 times a 2b plus 1, and there's another name for the number 1. So then our final result then is going to be equal to what? b minus 3 over 2b minus 1. Again, remember that our denominators cannot be 0, so therefore b cannot take on values which will make that denominator 0. Namely, in our first expression, b cannot be negative a half, and here b also cannot be positive a half. Is that right? In order to have this statement true for all values of the variable. Well, let's look at our last example. Here we have 1 plus a over a minus 1 times 4 plus 3 over a squared minus 1, all raised to the negative 1 power. Now, the only factor that's raised to the negative 1 power is this one right here. So this then is going to be equal to, well, let's just repeat this term, this factor rather, times, and let's use our definition or our theorem, which says that what? This is x raised to the negative 1 power is 1 over x. Is that right? So it's 1 over, and there you have 4 plus 3 over a squared minus 1. Now, let's use our theorem, which says x times 1 over y is equal to x over y. Is that right? So then in our numerator, we have 1 plus a over a minus 1, all divided by 4 plus 3 over a squared minus 1. Now, let's look at this and think of this as times 1. And what I'd like you to do now is to pull out of your hat some name for this number 1, which is going to help you simplify this expression. And you look at this and you say, well, I think it's going to be the least common denominator. This is 1 over 1, and a minus 1, this is 4 over 1, and this is a squared minus 1. So what's the least common denominator of those 4 numbers? And it's going to be, Bill?
A squared minus 1.
A squared minus 1. So another name for the number 1 that we're going to put in here is?
A squared minus 1 over a squared minus 1.
Good. All right, everyone see that. All right. Now, if you approach this problem in this fashion, rather than thinking only of this part, then only of this part, then simplifying and what have you, if you approach it in this way, I think it's going to come out much more quickly for you. Now, you're going to use your distributive property. You have a squared minus 1 times 1 is what? A squared minus 1. Plus, now here we have a squared minus 1, which we know factors into a plus 1 times an a minus 1, divided by an a minus 1, and there's a name for 1. Is that right? So whatever is left is what? We have a times, well, let's include that step. We have a times what? A plus 1. Divided by, now here we have a squared minus 1 times 4. So let's include that step. That's 4 times an a squared minus 1. Plus a squared minus 1 times 3 over a squared minus 1 is 3. Okay, now let's clean up that numerator a little bit. Well, here we have a squared plus a squared is 2a squared minus 1 plus a. Is that right? So let's put the plus a minus 1, and possibly there's a trinomial which we can factor. In the denominator, we have 4a squared. Is that right? Now here we have minus 4 plus 3 is minus 1. And you say, aha, I can factor that. Now, let's look then at the numerator, and possibly that's going to factor. We have 2a times a is a 2a squared. And what number can we put here? This is a plus 1, is that right? That's a plus 2a. And what? A minus 1 is minus a, is a plus a there. And sure enough, it factors. And what then will the denominator factor into? What do we have there? 2a minus 1 times 2a plus 1. And again, the problem is rigged. There's a name for the number 1, and this then is going to be equal to a plus 1 over 2a plus 1, and that then is our final result, the most simplified name for this original expression. All right? Let me give you your homework assignment. This will be assignment